First, I would like to thank Julio for inviting me to give a talk within this session, which already has very fantastic talks. And here I'm going to talk about not a predatory behavior, but a defensive strategy. And I'm going to present the results that we have, a study that we have conducted recently together with one bachelor student, Yudun Tsai from Taiwan, and my colleague Radek Michalko. I think you know very well that spiders has many predators, and therefore they have evolved different types of defenses, either primary or secondary, such as crypsis, camouflage, or Batesian mimicry. And I'm going to focus now on the Batesian mimicry. And by definition, this means that the spider is imitating phenotype of a noxious model. And quite many species have been recognized in spiders to be Batesian mimics. And some of the species imitate, for example, beetles or snails, but actually most of the species are imitating ants. However, the morphology of ants and spiders is different. You know very well that spiders have only two body parts, the prosoma and opistosoma, while ants have three body parts, the head, thorax, and abdomen, or gaster. And this is resolved by having some constriction. Spiders also have 4 pairs of legs, while ants have only 3 pairs of legs and antennae. And this problem is resolved actually by raising the first pair of legs and imitating the antenna. But yet there is another problem that spiders have to face, and this is the different post-embryonic development. Ants are imagos. I mean, they are whole metabolous insects. So the ants that we see being active on the ground are actually not increasing in size. They have a fixed size. But spiders, they grow slowly and they change their body size markedly during the post-embryonic development. So ant-mimicking spiders have to face this problem, and there is a solution which has been actually observed some 70 years ago, first by Matthew in 1945 and then by Reiskind in 1970. And they found that actually ant-mimicking spiders shift their models. So here you can see an example, a salticid spider of the genus Zuniga. When it's juvenile, it's imitating small Camponotus ants, and when it becomes adult, it shifts to another ant of the genus Pseudomyrmex. This shift in mimetic models has been coined as transformational mimicry. And actually, transformational mimicry is not only occurring in spiders. Some other ant-mimicking insects actually also transform. For example, mantises or many heteropterans that imitate ants, or even phasmatodians. So all these mimics actually shift between the models, and this could include either 2 models or 3 or even 4 models, depending on the size difference that they actually have to go through during the development. It hasn't been, however, known how accurate are these mimetic, or how accurate are these different stages of the development. And according to the recent theory proposed by Penny in 2012, it says that the early instars should be rather inaccurate mimics, while the late instars, or the adults in this case, should be accurate mimics. And this is because early instars are too small and thus unprofitable for many predators, for example, birds. So this theory would hold true only if the predator is constant. That means both the early juveniles as well as late juveniles and adults are under selection of the same large predator. However, we have seen many times, and this is a work of many different people, that shows that actually spiders are, during their ontogenetic development, are predated by many different predators, not a single one. And therefore, the early instars as well as could be as accurate mimics as the late instars or as the adults. And this could be either because these early instars are occurring in different seasons of the year than the late instars, or in different microhabitat. So they are populated by different predators. So basically, all of the instars have to be efficient in protecting themselves. So our aim in this study was actually test the hypothesis of transformational Batesian mimicry in an ant-mimicking jumping spider. And particularly, we were interested in the question whether these different instars are actually similarly accurate and whether they are similarly protected from predators. To do this, we selected one single species, Leptorchestes berolinensis, which is one of the very few ant-mimicking spiders which are occurring in Central Europe. And actually, in this species has quite accurate mimicry. This is the adult male, and this is the juvenile. We observed or measured the mimicry in both sexes. That means adult males, adult females, and then small and big juveniles. The small juveniles include the first 3 instars approximately, while the big juveniles include the next 3 instars. These spiders occur on a bark of these old dead oak trees, which are common in certain area in the southeastern Czech Republic. And on these trees, they co-occur together with several ant species. Named these ones, this is Camponotus vagus, which is quite large and attaining the body size of up to 1 centimeter. Then slightly smaller ant, Lasius fuliginosus, which is attaining the body size of about 6 millimeters. And then 2 small ant species, Colobopsis truncata and Dolichoderus quadripunctatus, which attain the body size of between 3 to 4 millimeters. I forgot to say that the adult body size in Leptorchestes is between 6 to 8 millimeters, and the small juveniles are about 3 to 4 millimeters. So first, we actually assess the phenotypic similarity. And because mimicry is multi-trait, we conducted several analyses. So first, we measured the movement, because ant-mimicking spiders are known to imitate not only the shape and coloration of the ants, but also their movement. And for this reason, we have recorded the movement of both mimics and models by etovision. Then we use spectrophotometer to record the exact coloration of their body. And finally, we focused on 2 traits. First, the body sizes, which included the total body size, as well as size of particular body parts and thickness of the legs. And shape, that means the total body shape, which means how actually accurate the ants, the spiders are imitating the body shape. That means head, thorax, and gaster of ants. And then we look at the selection by predators, and we actually use 3 different predators. First, we look at the perception of the birds. That means we modeled visual perception, how the birds can see the mimics and models. And then we performed predatory trials with 2 invertebrate predators that are occurring syntopically and symmetrically with the spiders. For adults spiders, we use Mantis religiosa, which is a common mantis and the only mantis that occurs in Central Europe. And for the juveniles, we use Pisaura mirabilis, because juveniles occur in autumn when mantises are too big to be potential predators. And here I'm going to present the results. So first, we look at the comparison of the movement. We use principal component analysis to actually visualize in ordination space the similarity between the mimics and the models. So this means 4 different mimetic stages: small juveniles, big juveniles, adults, females, and adult males, and 4 different ant species: Camponotus, Colobopsis, then Dolichoderus, and Lasius. And as a control, we use non-mimicking spider species of the same family. So from this picture, you can clearly see that the movement characteristics of the mimics and models were very similar and very much different from the control, that means from the non-mimicking spider. And that the dots, or actually the points, have overlap markedly. So that means movement of adults was mainly similar to Camponotus ants, while the movement of juveniles was mainly similar to Colobopsis ants. Then we compare the body shape, and we see actually a similar picture. You see that the body shape of the mimics is similar to the body shape of the ants. Again, these polygons overlap, and this is very much different from the control. That's because these spiders have false constriction on their abdomen, which imitates the free body parts of ant body. Then we look at the size measures. And so what you see is that actually the different the small or the juveniles have actually much smaller body size than the adults, of course, and therefore their polygons overlap with the small ants, while the males, which are in the mid of a medium size compared to females and juveniles, they overlap mainly with Lasius ants, which are the medium-sized ants, and female are more closely to the largest group of ants of the genus Camponotus. And finally, we compare the body the coloration. And what we see again is that the coloration of all these mimics and models is very much different from the control, because all these mimics and models actually are basically almost black with some white spots only. And we can see also some overlap that, for example, females are overlapping mainly with Camponotus and males with Lasius ants. So then we actually combined all these four traits in a final overall PCA analysis in order to incorporate all of them into a single analysis. And we get this picture. So what you see here is that females are most closely or most similar to large Camponotus ants. Males are most closely associated with Lasius ants. And then the small juveniles are rather closely associated with medium-sized ants of the juveniles or of the Colobopsis genus. The control spiders are very much different. What we can see clearly here that the adult phenotype is actually much more similar to the ants than the juvenile phenotypes. And this would agree with the previous theory that the juveniles are more inaccurate phenotype. So we have the results of the similarity, and now we look at the selection by predators. So first of all, we used color discrimination or the visual discrimination or the visual modeling of a common bird predator. For example, the blue tit, which is very common in this area. And we did this modeling separately for the juveniles and then for the adult mimics. So if you look at the juveniles, actually I have to explain what the figure shows. So on the ordinators are color contrast values. Which means how different is the mimic from the model in coloration only. Nothing else is considered here. And the bars are showing basically whether if the bars are above the unity, that means the mimics are not distinguishable from the models. But if the bars is above the unity, like in this case, that means the birds can easily discriminate mimics from the models. So if you look at the first picture of the juveniles, we clearly see that when they are compared with all three potential ant models, that means Colobopsis, Dolichoderus, or Lasius, they are basically not distinguishable from ants. But the control spiders are easily distinguishable from the mimics. And if we look at the adult mimics, where we separately estimate or assess the anterior and posterior body parts. So when we look at the picture or the results for the males, we clearly see that the males are easily distinguished from the control spider by the birds, but not from the Lasius ants. And the results for the females are slightly different. The anterior part, that means prosoma, is not distinguishable from the ants. That means it has similar coloration. But the opistosoma has slightly different coloration, though it's at the verge of significance, because the confidence intervals almost includes the unity. So this clearly shows that the juveniles are actually, for the perception of birds, better mimics than the adults. And then we conducted predatory trials with two different predators. For juveniles, we have used as a predator Pisaura spiders, and we conducted these experiments with constrained randomized design. That means that the predator first was offered an ant, and then either a small or a big juvenile and a control spider. As a control, we have used Philodromus spiders. The figure here shows what's the probability of attack and killing either the model, in this case the Lasius ants, or the mimics, small and big juveniles, and the control spider. And the picture is pretty clear. While Pisaura has frequently attacked and killed control ants, it has never attempted to attack either the model or the mimic. When we get to the adults, we use as a predator mantis, And again, the design was the same, constrained randomized design. That means, again, in this case, as a model, we have used Camponotus ants, and as a mimic, both adults. That means both males and females. And as a control, we have used similarly sized Pardosa spiders. And again, mantises has frequently captured Pardosa spiders, but they have rarely attempted to attack either the model or the mimic, and never has actually succeeded to catch either the model or the mimic. I will now show you a short video that shows the behavior of the mantis. So mantis is hanging on the straw, and the mimicking spider is coming up the straw. It's waving the forelegs. This is an adult male. You see that it's waving the forelegs to imitate the ant antenna. And it soon will get to the other part of the straw, where the mantis will try to attack. You will see soon the attempt. Yeah, now there was a short attempt, but then actually recognize that it's a rather something unpalatable, and it jumps away. So leaving the spider alive. So let me conclude. So our study shows that Leptorchestes berolinensis is a Batesian mimic of ants, and that actually all developmental stages imitate ants. In this case, the spider is undergoing transformational mimicry, and it's shifting between two sympatric ant models. Juveniles imitate Colobopsis or Lasius ants. That means Colobopsis is imitated by the small juveniles, Lasius by the big juveniles. And adults are imitating Lasius and Camponotus ants. Specifically, males are imitating Lasius and females Camponotus ants. Our study of the overall phenotypic analysis revealed that adults are actually more accurate mimics than juveniles, but the visual modeling of birds and also have showed the reverse. That means that juveniles are better mimics than adults. And the response of predators reveals actually that both juveniles and adults are accurate mimics, well protected from the predation. So I would like to thank you for your attention, and I would like to say that this public has been recently published in the American Naturalist. So if you want to see more details, just go to that paper. Thank you for your attention.
Thank you very much.